thing that we're going to add now is called a buffer. So I mentioned the buffer is mostly distilled water, but it also has magnesium salt. So the magnesium salt will break down into ions, and it will help us conduct the electrical charge and prevent the gel from melting. So the buffer is in the clear flask that you have on your table. Each group is getting 250 milliliters. You're going to pour that into both sides of the box and over top of the gel in the middle. But go slow because you don't want it to overflow. So you'll use most of it, but don't overflow your box.
So what point is your
Yeah, this
So it says 200 250 is
I don't know what you're going to use most of it. So
it should be around
go too fast.
Overflow this part or
and then pour a little.
it's like really high.
okay.
Oh, yeah. Here, I got it because I have the.
Okay,
so you got it? Yeah. Can you just put it in like this?
Pour a little on top of the gel to make sure the well's
On the black side?
Yeah, no. Oh, there should be a little over the jelly.
So it's got to kind of like wait over the gel a little bit. When you fill out the sides.
Oh, fill up the Stop. Wait, okay. Keep going.
Wait, I can't record it.
So keep on going.
I might want to get it just to fit on.
No, over the gel, yeah. I think you'll need a lot of that. Yeah, no, it should come up the other side, yeah. Yeah, so.
Okay, good.
I think you're fine. Yeah. There's a layer on top, right? No, both sides. See, electricity has to flow. And so this is your dump.
Did that come out of the tray or?
So this is the base.
Perfect.
There should be a layer over your gel. Otherwise, the way it under my brain, it won't feel the same.
It's way harder to pipette into the gel than it is to pipette onto the wax paper. Okay? So listen for a moment. When you're pipetting into the gel, it's important to keep the pipette straight up and down. Have you ever played the game Operation?
Yeah.
Okay, what happens if you touch the sides in Operation? Yeah, and I heard someone say it. Okay, good. So keep that in mind, not to make you too anxious, but you're trying not to stab the sides or the bottom. Okay, you should probably be making motions this big while you're pipetting either. But if you stab the sides or the bottom of the well, then you're going to make a hole where your DNA will get stuck. The gel will fill the end of your pipette tip like a cork, so you also might have trouble pushing out the liquid that you have. Okay, but we're practicing first so that you can get used to it before we have our samples. So you'll get a pipette tip the same way. Just by pushing your pipette into the tips, and then you'll, again, just as a reminder, push to the first stop, put the tip into the food coloring, let go of your thumb, and then pull it out. But when you pipette into the gel, keep the pipette tip straight up and down. You want the tip to go into the well, so it's actually okay to sort of feel the sides of the well to make sure you're in there. Just don't stab sideways. And then push down to the second stop. Lift your whole arm up out of the gel and then let go of your thumb. So if you let go of your thumb too early, you might pull your sample back up and you also might mix it together with the buffer. So just one more time. You get your liquid the same way, push the first stop, put the tip into it, let go of your thumb, pull it out, When you pipette into the gel, hold the tip straight up and down. Put the tip into the well without stabbing the bottom. Push all the way down to the second stop. Lift up your arm and then let go. Okay, so we're going to practice with the food coloring, still 7 microliters, but only in the 4 wells from the right. Okay, so here's a diagram of our gel. You have 8 wells, only practicing these 4, but you can practice more than once in each of those 4.
You can't.
So you're gonna do
Oh, where's the No, that's fine. Or unless you want to actually.
Okay, so first 4 from the right.
Go into the well. Not knowing.
If you're having trouble seeing the wells, the well will look a little bit darker than the gel around it. So if you're looking down on it, it should look a darker line.
Yeah, I see it, but like there's the whole. Yeah. So you bring it to slit. In between the two or like.
I want to see that it landed.
It's always my best.
Into the well.
But not stab.
Push it.
Yeah. 7. Right? And then you press it when you get inside. No, you put it here. And then you get it back over here. Touch the bottom, right? And then you would make it out. And this is a first coloring. Please, it's not real. You do the first one.
Yeah, make sure your hands steady.
It doesn't look like it went down that far. But she said you can do it again.
Watch your hand, Jackson.
Yeah, we did the first one. So ours just before. No, she said we can practice on it.
Oh,
She said we can do it again and again.
the real DNA.
Yeah?
No pressure. No pressure. Once you have a feel, right, like, you know, how much you should go.
Oh, yeah, she can practice the first word.
We only want the supernate, so it's important to put your pipette tip only into the clear liquid at the top, not all the way down into the bottom. So, do you see your 2 really tiny tubes in your test tube rack? Okay, those little bitty tubes, those are called PCR tubes. So there is a small amount of liquid in the bottom of those, and those are primers. So the one that looks green has primers that will recognize sequences common to all plants. So this is like our control. Basically, this will let us know that the DNA extraction worked and that the PCR worked. So that has plant primers in it. The other one that looks kind of pink, that has the primers that recognize these sequences in GMO crops. Okay, so we need to add some of our sample to those primers. So let's add 5 microliters of the supernatant from your sample to each of those small PCR tubes. So 5 of your supernatant from your food sample into each of the small PCR tubes.
I'll open up the tubes.
Make sure you change the
I'll do
tip
the
in
super
between.
name.
Change the separate. Change the separate.
Oh, 5 of the oats.
So 5 of just this top side, right?
Don't want to get
Did you adjust?
Do I not?
So 5 of them.
And then 5. No, wait, check it out.
Just in case you guys
Okay, and then you guys can close them and then tap them onto the table to mix it up.
This follows.
No, that's what I wrote on the board of your.
I feel like the things mixed into the
So do we just like one of these?
That I took your samples and have replaced them with other samples. So the next step of the process is to do PCR. Does anyone know how long it takes to do PCR?
20 minutes.
That's bacteria.
It's quick.
Not quite days. Okay, it takes a few hours depending on how many repetitions or how many repetitions you want. So we usually run them for 2.5 hours. So rather than waiting 2.5 hours, we're fast forwarding through the next
It's
step.
like the kitchen.
So the
cooking show.
samples that you have now have already been through PCR, so the DNA is amplified in those. Okay, so do you see how one of them says P on the top and the other one says GM?
Yeah.
Okay, for the next step, we're going to add something that will change the color, so you'll need to know the letter to know which one is which. Okay, so did you notice how the green food coloring was floating up out of the wells in your gel?
Yeah.
Okay, so the green food coloring doesn't weigh enough to keep it in the well on its own, and neither does the DNA. So we're going to add something called a loading dye. The loading dye contains sucrose, which will weigh it down, and then also dye so we can see it as it runs. So there's one tube of loading dye on each table in the middle. It says LD on the top. And we're going to add 5 microliters of that to each of the small PCR tubes.
Ready?
How many guys?
You okay.
How many guys?
5.
In each of those?
Where are we adding it
Ready?
Just don't cross me down. For both, yeah, for both.
Just add 5.
Into each.
Yeah, I think so.
Nanometers? Did you think nanometers? Did you try it?
Okay, so make sure to just shake it.
It's 5, right?
And then 5 microliters.
Oh, yeah, if you flip it upside down, it probably takes
That's what I put.
That'll take a minute.
Change slips.
And just tap them onto the table to mix it up.
this
Wait,
like.
how are you doing?
No, it's not.
It's like, how are you?
Different values actually matter, but it's not quantitative.
Oh, that's so cool.
Oh my god.
Oh, and the, yeah.
So once the loading dye is added, then we're ready to load it into the gel. Okay, so this is where it becomes important which one says P and which one says GM. Because the sample that has plant fragments is going to go into the first well from the left. We're going to skip one because we don't want to load them on top of each other. This is just to make sure we've got some good space in there. And then the GM sample will go in the third well. I'll also bring you another thing, the ladder. So the ladder is like a molecular ruler. It has DNA fragments of known length in it, and that will allow us, if we want, to figure out how many base pairs long our fragments are. Okay, so 10 microliters of P into well 1, and 10 microliters of GM into well 3.
12.
So you can use that as a diagram.
Oh, well, P's.
P goes into the first one, you skip one, and then
Yeah, GM?
No, I thought, yeah, that one.
no, that's a 12 for one of them.
12, 10 is the P, right?
The ladder is 12.
Yeah, the ladder.
The ladder is not there. The ladder is limited. So they both are yeah. Oh, they're all the same. Can't switch. Here, you can't switch.
Yes.
I'll switch it.
Is it 10? Does this look like 10? It says 10 and 10. Where do you go?
Press down.
In the
Take
first
it
one.
out and then
The first one, right? It's the P. You sure? Make sure you don't hit the bottom of it. No, don't miss one yet.
take it off.
Okay, where do I go? Right here? Can't really see it. Wait. You guys got a bubble.
So I see some in here. You probably have enough. So the last thing that you need is the ladder. So I just need one pipette from each group, set of 5. Okay, grab a tip.
Yes, I mean, well,
So basically in between the...
So not on top of your sample. Okay, what's going on? So it's in the second one. That's okay. You can put this in either the third or the fourth one, as long as you've got the plant first and then.
Yeah, that's half of what we're putting in the other one.
Yeah, just make sure they're not on top of you.
Is the biggest height, right? So the base there is 2,000. And this one ran the most, right? So it has only 100 base pairs. Alright? So take a picture of that, and that's the normal ladder.
Set one of your pipettes.
I mean, or I can send it to you. It's the same thing. But you just have it.
Yeah, make sure you line it all like a black, red with red, and then lower both ends of the same. Yeah, black with
You're gonna put the lid on top, and then match that up with the power source on the back.
Oh, in the machine.
Just check and make sure it's close tight. And then once it's close tight, you can plug it into the power source. So line up black with black and red with
As long. So you have to match red with red.
Yeah, I think the one.
Power source? Okay, good. So we're going to start running our gels. So reach over to the side of the green power source and press the on switch. All right. So as it gets started, once it turns on, is yours on? Yeah, go ahead and push that.
That's on the right.
All right. Okay, so once it's on, you should see a 0 or a blinking cursor at 0V, depending on which kind you have. Can you see that? All right, good. So that's the voltage. Okay, we want to set the voltage to 120, and to do that, you can press the up plus button. You can hold it down to make it go faster. 120. Hold it down. So once it's set at 120, we're going to start our run. So you can press the running man button.
Oh,
So press the running man button.
Ooh, snap, that's cool.
Okay, good. So once you press the running man button, you should start to see bubbles coming up at the end of the box. Do you see that? Yeah. Anybody got bubbles?
Yeah.
Anyone not see bubbles? All right, good. Okay, so the run has started. We're going to give it about 18 minutes to finish. So it'll take a little while, but you'll start to see the dye moving through the gel. Once that's done, we can't actually see the DNA with our eyes. So when the gel was made, we also added something called CyberSafe, which makes the DNA glow. But it glows under UV light. So once they've run, we'll collect them and then we'll image them with a UV camera. Okay? All right. So let's talk a little more about gel electrophoresis. Do you notice how the box has two different ends? So there's a black end and a red end? Okay, the black end is the negative end of the box, and the red end is the positive end. So it's kind of like a battery. All right, so when we plugged it in, we created this circuit with the power source. So the electricity will run through the gel box. One reason why it was important to line up black with black and red with red is because if you do it opposite, you create a little mini circuit inside of the power source, which could make it catch on fire. No, we don't want to do that. Well, it'll probably just get overheated and turn off first. But we had to be safe. All right. Okay, so does anyone know what charge the DNA has?
Negative.
Negative. Okay, so we put the DNA in at the negative end of the gel. So what will happen as the electricity flows through?
It'll be attracted to the positive side.
Good. It will be attracted to the positive end. Okay, but not all the DNA moves at the same pace. So can I get one volunteer? All right, I saw your hand. Come to the front. Okay, you are going to represent a short fragment of DNA. So all I need you to do is just walk from me to Alejandro in the middle of the chairs. Okay, go ahead. Go quickly. Go. All right. Okay, now I need 5 volunteers. Okay, 1, 2, 3, 4, 5. All right, so you 5 are going to hold hands in a straight line, and you are representing a long back. So I just want the 5 of you to walk through the chairs to the back of the room.
I got the target your skills. Bam.
All right. Okay, so everyone can take a seat again.
Sounds good.
Okay, who moved faster, the short fragment or the long fragment? Long fragment organized themselves pretty quickly, so you weren't as delayed as I had hoped. But the DNA doesn't really do that. They don't look at each other and say, okay, cool. So if you were a DNA fragment, you would get stuck as you went along. So in the gel, there are tiny microscopic holes. They're called pores, so it's sort of like a sponge. The short fragments can maneuver easily through the pores and can move further in the same amount of time. But the longer fragments get stuck on the sides of the pores as they move through, so they don't make it as far. So you can tell how long the DNA fragment is by how close it is to the top of the gel. Okay, so if we looked at this drawing of a gel I have here, which fragment is longer, the one in lane 1 or in lane 3?
Lane 3. Lane 3.
Lane 3, right. So longer will be closer to the top because they didn't move as far. And shorter fragments are closer to the bottom, they move further. Does that make sense?
Yes.
All right. Okay, so again, it will take a moment for this to happen. We'll give it a few more minutes. But while we're waiting for our gels to run, let's talk a little bit more about GMOs. So what are some of the reasons why people might genetically modify crops? You mentioned a few of them to me. You said there could be higher yield, they might grow faster. What else? Yeah.
If it's being like attacked by a certain other organism, you want to make it so that it's resistant to that organism.
Like what's an example of that you were thinking of?
Tomatoes and beetles.
Okay, so if there are pests that eat the crops, then you might want to make them resistant to the pests, that make them taste bad to the pests, right? So there's natural pesticides that can be engineered into the crop. Yeah. Longer shelf life. Good. Yep.
In some areas of the world, not use such fresh foods, so it's easier to produce genetically modified
Yeah. So have you heard of golden rice?
Yes.
So golden rice is a genetically modified crop that's been engineered to have vitamin A in it. So in countries where there's a high rate of poverty and a high reliance on rice, there's also a higher incidence of eye problems, of blindness. So this engineered rice gives you the nutrients that you need to have healthy eyes, even if you're only getting access to rice as your food source. So that could be a beneficial thing. It could improve health. Yeah.
Preference of watermelons versus seeds.
Yeah, so you could produce seedless foods if you want them to be that way. Mm-hmm. Yeah.
I also think of us that there's prone to droughts and you have crops that require a lot of water and also to require less water.
Yeah, so you could engineer them to be like thrifty in terms of their water usage. Okay. Let's see. What about disease? You thought about that? Okay, who likes bananas? Okay, so did you know that the bananas that we eat now are not the same kind of banana that people used to eat in the past? Okay, so the previously preferred type of banana actually went extinct because of a fungus. So in the earlier part of the 20th century, there was like a creamier, sweeter banana that people ate. But bananas are grown from cuttings usually on plantations, so they're all genetically identical to each other. They're clones. So if you have all the same variants of a gene within a whole population, then there will be some individuals that are resistant to a disease. So variation is necessary as a population if you want to be able to bounce back from that type of attack. But the bananas that we eat now, they're called Cavendish bananas. They're also produced the same way. And actually on a few islands where bananas are grown, they've already had an issue with a new type of fungus attacking them. So there's a concern that this type of banana might actually be wiped out as well. Kind of a fun aside, have you ever wondered why like Laffy Taffy and other bananas, like artificial banana flavored things, don't taste like bananas?
That's so ridiculous.
They taste like the old kind of banana. So, yeah, so they were engineered to taste like the type of banana that was wiped out. I forget the name of that variety. And for some reason we haven't made a new artificial banana flavor that tastes like the Cavendish, but that's kind of lagged behind. All right, so if you've got that lack of variation, then you could be wiped out. Have you heard of something called the Red Queen hypothesis by any chance?
Yeah, discussed
You
it.
have? Okay, what does that mean?
What do we remember?
Yeah.
Let's say it's like a virus and a bacteria. As the bacteria, like the population, like the ones that are able to survive like the effects from the virus are being selected for, the viruses that are strong enough to stay with the strong bacteria are also being selected for. So it's co-evolution.
Good. Yeah. So it's a theory to explain coevolution. It comes from Alice in Wonderland. He said you mentioned this, but there's I always paraphrase this. I need to look up the exact quote, but the Red Queen says something like, "You have to keep running just to stand still." To Alice. So that's the idea. It's an evolutionary arms race. So as plants are engineered to be resistant to the things that infect them, the things that infect them are also evolving. So it's not a one-off change that you have to do to make it resistant to the disease. Have you talked about the Irish potato famine in school?
Let me read
Okay. Yeah, so what happened in the potato famine?
Since they didn't really have much variation in their potatoes, things went got attacked home. That attacks really potatoes.
Right, and the disease that attacks the